Hello, everyone. We are starting chapter 13 this week. We're going through chapter 13 and 15.1. So we're going to start with chapter 13 and then end at 15.1. And then next week, or not next week, sorry, the week after next is when we'll move on to chapter 14 and the rest of chapter 15. So in chapter 13, we have 4 sections. They are chemical equilibrium, equilibrium constants, shifting equilibria, Le Chatelier's principle, and equilibrium calculations. So just to start off, to get your minds thinking, we've got a picture of a vein here and showing carbon dioxide being transported in the body. And it's got all these different reversible reactions, and that's what these arrows here symbolize. So this is an example of an equilibrium, and we're going to talk about what exactly an equilibrium is and look at a lot of different calculations and predictions we can make with them. So we're starting with 13.1, chemical equilibria. In this section, we're going to describe the nature of equilibrium systems and explain the dynamic nature of a chemical equilibrium. So to start off, if you have reactions that have an appreciable reverse reaction, they're represented with an equilibrium. Okay, so like this reaction here, N2O4 and NO2. So what's happening is N2O4 is becoming 2NO2, but also 2NO2, so those two NO2s are reacting with each other to form N2O4. So what's happening is this is going back and forth. And eventually, when these rates are equal, they reach what is called equilibrium. So with this reaction, N2O4 is a colorless gas, whereas NO2 is brown. So if you were to take a container and you put N2O4 in it, close it, and heat it up to 100 degrees Celsius, you would notice that a reddish brown color starts to develop, and this is because NO2 starts forming. So this is the forward reaction. So that's what this top half arrow represents, is the forward reaction. Now, once we get enough NO2 built up, you can get them reacting with themselves to form N2O4, and that is the reverse reaction happening. So these two reactions are actually happening at the same time. So when we hit equilibrium, the rate of each reaction is the same, and the amount of the reactants and products stop changing, but the reaction is still going. But if you were to have something that could measure the concentrations of everything, it would stay the same. Okay, so you can think of this as like people coming and going out of Target, for instance. At equilibrium, the amount of people leaving and coming in, those rates are equal. They're not changing, but there's still maybe a different person coming in while a different person leaves. So this is a nice visual looking at that N2O4 NO2 reaction. And what's happening, you can see here, is changes in the concentrations over time. So in A, it's just kind of showing us at T0. So when we first start it, all we have is N2O4. And it starts reacting before we hit equilibrium. And you've got N2O4, you've got some NO2s here. And then these NO2s now start reacting with each other to form more N2O4. So at equilibrium now we're here. In B, what you see is the changes in the concentration over the N2O4 and the NO2 eventually stop changing. It doesn't mean the concentrations are equal, okay? It just means that they stop changing. So the NO2 goes down in concentration, since that's what we started with, until eventually it evens out. So here you can see there's no change in concentration. Same goes for the NO2. It starts increasing and increasing, and then it gets to a point where it doesn't change. So that means we're at equilibrium. The reaction is still happening, but the concentrations overall are not changing. Graph C is also showing equilibrium, but this is looking at it in terms of the rates of the reactions. So you see their individual rate equations, Kf times N2O4 versus Kr for reverse at NO2 squared. And you can see these rates changing until eventually they hit equilibrium, and those graphs are right on top of each other, showing that the rates are equivalent. Now, the rate of the reaction is going to start out fast, as you can see from the graph. Looking at the N2O4, you can see that it's kind of got a bit of a steep slope there. But it's going to slow down as the N2O4 decreases in concentration, because now you have less of it to react, so it's going to have a lower rate. Whereas the reverse reaction, the NO2 reaction, is going to start off slower because it doesn't have that much of it built up. But then it's going to speed up as we get more NO2. And then once we get to a point where the N2O4 it gets low enough to the point where the NO2 rate is high enough, or they're the same, then we have equilibrium. So nothing is going to change for the concentration of either gas until the temperature or the volume of the container is changed. So equilibrium does depend on temperature, because if you remember, the K constants depend on temperature. So a couple misconceptions. The amounts of the reactants and products are not necessarily equal to each other at equilibrium. So it's very important that you remember this. Equilibrium doesn't mean equal concentrations, it means equal rates. And then, although the concentrations of everything remain constant at equilibrium, it's not static. So the reaction is still happening. It's dynamic. It's just happening at equal rates where the concentrations overall are not changing. An example is these people juggling. Each person is constantly catching and throwing clubs at the same rate. Okay, and they're holding kind of constant number of clubs. So at one point, you know, this dude is holding 2 clubs. Okay. Physical changes are also can be reversible and can establish equilibria. For instance, this is bromine, and it's an equilibrium between its liquid and gaseous state. So you see the gas up here at the top of this ampule and the liquid here. So it's constantly going between the liquid and the gas phase. And you know, just to show you guys that it doesn't have to be a chemical process to be in equilibrium.